In this quick walkthrough, we will evaluate a definite integral step by step. Here is the problem. Evaluate the integral from 0 to 2 of 1 over x squared plus 1 dx. We will visualize the area, find an antiderivative, apply the fundamental theorem of calculus, substitute the limits, and simplify to the exact and approximate answers. First, the visual meaning. We draw axes, and the curve y equals 1 over x squared plus 1. The definite integral from 0 to 2 is the area under this curve above the x-axis between x equals 0 and x equals 2. Think of the area as the limit of lots of thin rectangles that perfectly match the curve. Step 1. Find an antiderivative. The derivative of arctangent of x is 1 over x squared plus 1. So the indefinite integral of 1 over x squared plus 1 dx is arctangent of x plus c. Step 2. Apply the fundamental theorem of calculus. The integral from 0 to 2 of 1 over x squared plus 1 equals big F of 2 minus big F of 0, where big F is an antiderivative. Using big F of x equals arctangent of x, we get arctangent of 2 minus arctangent of 0. Step 3. Substitute the limits. We write arctangent of 2 minus arctangent of 0. Since tangent of 0 equals 0, arctangent of 0 equals 0. So our value is arctangent of 2 minus 0. Step 4. Final result. The exact value of the integral is arctangent of 2. For a quick approximation in radians, arctangent of 2 is about 1.1071. This numerical value matches the green shaded area from 0 to 2 under the curve. Recap. 1. Identify the antiderivative arctangent of x. 2. Apply the fundamental theorem. Evaluate big F of 2 minus big F of 0. 3. Compute arctangent of 2 minus 0. Answer. Arctangent of 2, approximately 1.1071. And that is the complete, quick, and intuitive solution to this definite integral. In this short lesson, we'll compute, step by step, the expression e to the natural log of 2 to the third power. Our goal is to use basic log and exponential rules and give you a fast visual cue for future problems. Step 1. Identify the inner logarithm. Inside the exponent we have natural log of 2 to the third power. Using the logarithm power rule, natural log of a to the b equals b times natural log of a. Apply it here. Natural log of 2 to the third power equals 3 times natural log of 2. Therefore, our expression becomes e to the power of 3 times natural log of 2. Step 2. Use the fundamental identity e to the natural log of x equals x for any positive x. We can apply it in two equivalent ways. First way, directly undo the natural log. E to the natural log of 2 to the third power becomes 2 to the third power. Second way, rewrite e to the power of 3 times natural log of 2 as e to the natural log of 2 all cubed, which becomes 2 cubed. Both paths lead to the same expression, 2 to the third power. Step 3. Compute the remaining power. 2 to the third power equals 2 times 2 times 2. That multiplies to 8. So, the final value of e to the natural log of 2 to the third power is 8. Visual shortcut. Whenever you spot the pattern, e to the natural log of parentheses, something, close parentheses, you can immediately replace it with that something, then compute the simpler value. Here, e to the natural log of 2 to the third power becomes 2 to the third power, which equals 8. We will simplify, step by step, the expression square root 50 times square root 16, all over square root 8. Each line appears exactly when we say it. Step 1. Product rule. For square roots, the square root of a times the square root of b equals the square root of ab. Apply it to the numerator. So the numerator becomes the square root of 50 times 16, which is the square root of 800. Keep the denominator as square root 8. Step 2. Quotient rule for square roots. The square root of a divided by the square root of b equals the square root of a over b. We will use that on our fraction, so it becomes the square root of 800 over 8. Now divide inside the radical. 800 divided by 8 equals 100. Step 3. Evaluate the square root. The square root of 100 equals 10, because 10 squared is 100. That is our final simplified value. Quick visual cue. 1. Combine the numerator roots to get square root 800. 2. Use the quotient rule to get the square root of 800 over 8 equals the square root of 100. 3. Evaluate to get 10. In this lesson, we evaluate the integral of the square root of tangent of x, step by step, with no step skipped. Step 1. Set up the integral. We want the indefinite integral of the square root of tangent of x with respect to x. Step 2. Use the substitution u squared equals tan of x. Differentiate both sides. 2u times 2 by dx equals secant squared of x. But secant squared is 1 plus tangent squared. Since tangent is u squared, secant squared becomes 1 plus u to the fourth. Solve for dx to get 2u over 1 plus u to the fourth times du. Now substitute into the integral. The integral becomes the integral of 2u squared over 1 plus u to the fourth du. Step 3. Decompose the rational function. Write 2u squared as the sum, u squared plus 1 plus u squared minus 1. Then split into two integrals, I1 and I2. Step 4. Evaluate I1. Divide numerator and denominator by u squared. Notice the numerator equals dv if we set v equal to u minus 1 over u. Then dv equals 1 plus 1 over u squared du. Also, u squared plus 1 over u squared equals v squared plus 2. So I1 equals the integral of dv over v squared plus 2, which is 1 over square root 2 times arctangent of v over square root 2 plus a constant. Back substitute v to get the expression in u. Step 5. Evaluate I2. Again divide numerator and denominator by u squared. Let w equal u plus 1 over u, so dw equals 1 minus 1 over u squared du. Then u squared plus 1 over u squared equals w squared minus 2. So I2 equals the integral of dw over w squared minus 2, which equals 1 over 2 square root 2 times the natural log of the absolute value of west minus square root 2 over west plus square root 2 plus a constant. Back substitute to write I2 in terms of u. Step 6. Combine the results. I equals I1 plus I2. Step 7. Substitute back to x. Recall u squared equals tan of x, so u equals the square root of tan of x. Replace u to obtain the final antiderivative. And that completes the problem, with every step shown and justified. We will compute 49 to the power negative 1/2, step by step. Here is the expression. Notice the exponent is negative 1/2. We'll use a rule for negative exponents first. Step 1. Rewrite a negative exponent as a reciprocal. The rule is a to the negative n equals 1 over a to the n. Applying this rule gives 1 over 49 to the 1/2. Step 2. Interpret the 1/2 exponent as a square root. The rule is a to the 1/2 equals the square root of a. So 49 to the 1/2 equals the square root of 49. Substitute that into our fraction to get 1 over the square root of 49. Step 3. Compute the square root. Since 7 squared equals 49, the square root of 49 equals 7. Step 4. Substitute and simplify. We replace the square root of 49 with 7 to get 1 over 7. Therefore, 49 to the negative 1/2 equals 1/7. Recap. Negative exponent gives a reciprocal. 1/2 is a square root. Square root of 49 is 7, so the value is 1 over 7. In this video, we will solve 125 squared minus 124 squared using the difference of squares idea, and we will do it step by step with quick visual cues. Here is the problem. Step 1. Recall the difference of squares identity. It says, a squared minus b squared equals, open parenthesis, a minus b, close parenthesis, times, open parenthesis, a plus b, close parenthesis. Step 2. Identify a and b for our problem. We choose a equals 125 and b equals 124. Step 3. Apply the identity to the expression. So we write 125 squared minus 124 squared equals, open parenthesis, 125 minus 124, close parenthesis, times, open parenthesis, 125 plus 124, close parenthesis. Step 4. Compute each factor. First, 125 minus 124 equals 1. Next, 125 plus 124 equals 249. Step 5. Multiply the two results. 1 times 249 equals 249. Therefore, the value of 125 squared minus 124 squared is 249. Optional check. Square each number and subtract. 125 squared equals 15,625. 124 squared equals 15,376. The difference is 249, confirming our answer. Intuitive cue. Consecutive squares differ by their sum. N squared minus, open parenthesis, n minus 1, close parenthesis, squared equals n plus, open parenthesis, n minus 1, close parenthesis. For n equals 125. The gap is 125 plus 124, which is 249. Here is a fast, visual solution. We will compute the value of square root of 50 squared plus the quantity square root of 50, all squared. We will use two undoing rules that pair a square with a square root. Undoing rule 1. The square root of a squared equals the absolute value of a for non-negative inputs. Undoing rule 2. The quantity square root of a, all squared, equals a again for non-negative a. Step 1. Identify each part of the sum. The first term is square root of 50 squared. The second term is the quantity square root of 50, all squared. Step 2. Simplify the first term using rule 1. Square root of 50 squared equals absolute value of 50. Because 50 is positive, the absolute value of 50 equals 50. Step 3. Simplify the second term using rule 2. The quantity square root of 50, all squared, equals 50. Step 4. Add the two simplified values. Square root of 50 squared plus the quantity square root of 50 squared equals 50 plus 50. That is 100. So the value is 100, with every step justified by the two undoing rules. In this quick lesson, we'll solve an indefinite integral step by step, with crystal clear reasoning and visuals. Our problem is the integral of x times log x dx. We'll assume log means natural log, which is ln, a common convention in calculus. We'll use integration by parts. The formula says the integral of u dv equals uv minus the integral of v du. Step 1. Choose u and dv using the LIATE guideline. Logarithmic, inverse trig, algebraic trig, exponential. Since we have ln of x times x, we choose u to be ln of x and dv to be x dx. So write u equals ln of x, and dv equals x dx. Step 2. Compute du and v. Differentiate u. Du equals 1 over x dx. Integrate dv. V equals x squared over 2. Step 3. Apply the formula. The integral of xl and x dx equals uv minus the integral of v du. Substitute the pieces. That equals ln x times x squared over 2 minus the integral of x squared over 2 times 1 over x dx. Simplify inside the integral to get ln x times x squared over 2 minus the integral of x over 2 dx. Step 4. Integrate the remaining term. Pull out the constant 1/2 to get 1/2 times the integral of x dx. That integrates to 1/2 times x squared over 2, which is x squared over 4. Step 5. Combine everything and add the constant of integration. So the integral equals x squared over 2 times ln x minus x squared over 4 plus c. We can factor x squared over 4 to get 1 fraction times the quantity 2l n x minus 1 plus c. Using the identity 2l n x equals ln of x squared, we can also write it as 1 fraction times the quantity ln of x squared minus 1 plus c. This is our final answer. Recap. Choose u equals ln x by liate, compute du and v, apply parts, simplify, integrate the easy piece, and combine.
In this quick lesson, we will evaluate the indefinite integral of the square root of 1 plus sine of 2x. Our plan is to turn what is inside the square root into a perfect square, simplify, and then integrate step by step with no skipped steps. Step 1. Use the Pythagorean identity. Sine squared x plus cosine squared x equals 1. We will substitute that 1 into the integral. So 1 plus sine 2x becomes sine squared x plus cosine squared x plus sine 2x. Step 2. Use the double angle identity. Sine of 2x equals 2 sine x cosine x. Substituting this in gives sine squared plus cosine squared plus 2 sine x cosine x. Step 3. Recognize the perfect square. Sine squared plus cosine squared plus 2 sine x cosine x equals the square of sine x plus cosine x. Therefore, the square root of 1 plus sine 2x is the absolute value of sine x plus cosine x. Step 4. Rewrite the integral using that simplification. The integral becomes the integral of the absolute value of sine x plus cosine x with respect to x. Step 5. Handle the absolute value. We must consider the sign of sine x plus cosine x. To get a clean antiderivative, we work on any interval where sine x plus cosine x is non-negative. So we assume sine x plus cosine x is greater than or equal to 0 on our interval. Then the absolute value drops. We integrate sine x plus cosine x term by term. The antiderivative is negative cosine x plus sine x plus the constant of integration. This is our result on any interval where sine x plus cosine x is non-negative. Important note, if your interval crosses a point where sine x plus cosine x equals 0, you must split the integral at those points.
We will solve the equation quickly and clearly using a clean visual cue for cross multiplication. Step 1. Write the equation and its domain restriction. The equation is the fraction open 3x minus 7 over x equals 2 over 7. Because x is in the denominator, x cannot be 0. Step 2. Cross multiply to clear the fractions. Draw the two diagonal products. Numerator 3x minus 7 goes with denominator 7. Denominator x goes with numerator 2. That gives 7 times the quantity 3x minus 7 equals 2x. Step 3. Distribute the 7 on the left. 7 times 3x is 21x, and 7 times negative 7 is negative 49. So we have 21x minus 49 equals 2x. Step 4. Move all x terms to the left. Subtract 2x from both sides. That gives 19x minus 49 equals 0. Add 49 to both sides. 19x equals 49. Divide by 19 to isolate x. So x equals 49 over 19, which is not 0 and is valid. Quick check. Substitute the value back into the original fraction. Left side becomes open fraction. 3 times 49 over 19 minus 7 over 49 over 19. That is 147 over 19 minus 133 over 19. All over 49 over 19. The numerator is 14 over 19. Dividing by 49 over 19 multiplies by 19 over 49, which simplifies to 2 over 7. The check passes. Final answer x equals 49 over 19. Thank you for watching. Tap like, share, and comment, then follow and subscribe for more quick problem-solving tips. Let's make maths simple. One video at a time only on Myverse Maths.